So instead of writing chronologically, I will just say some of the topological aspects of continuums. Like what is a continuum and what is connectedness. And all that, and then we did matrix Lie groups. So I don't know whether I said this so far, but this is not, most people will read it as Lie in English language, but this is named after a mathematician called Sophus Lie, who was Swedish, I think. He's from Scandinavia. So this is the name. And this work was done by him around the year 1900. So much later than the development of the discrete group theory, which was about 50 years earlier than that. Okay, so matrix Lie groups, and we saw that the big group there is GL n x, where x is R or C. N by n matrices of non-vanishing determinant, because you have to have an inverse, and correspondingly there is also SL nx, which have determinant equal to 1. So determinant is restricted not to 0. That is all you need for invertibility, whereas for the SL we restrict it to be +1. Okay, and then, so I am just going to do this quickly because we don't want to spend too much time. And then the so-called classical groups. According to Wigner and Weil. Wigner and separately at two different which is essentially metric preserving. Which contain things like SON and SUN and SPN, symplectic, SP2N typically. So this was our notation. So there are metrics in each of the cases and they are preserved by these groups. So this is what we did, and then the latest thing we were doing was representations of, so we got the angular momentum algebra. What we meant was rotation group. So which happens to be SO3, 3 by 3 orthogonal groups of determinant +1. And so here we worked out the generators. Lx, Ly, Lz, but then we said that we will define Ji, the complex notation, to be I times these. Sorry for the same I, we can make this into J. So J equal to 1, 2, 3. And then we found that the algebra is Ji, Jj equal to I epsilon ijk, Jk. So from this we can get, so then we found that SU2 has the same algebra. And in fact realized as the specific matrices Ji equal to tau I by tau 2, which are Pauli matrices. They satisfy exactly the same algebra. And then we could work out the representations. in other words, we found, so what does representation means? We found the set of states that completely realize the algebra. There are a set of states and eigenvalues on which the operators and their algebra are realized. So that is what we mean by knowing the representation, because we can then manipulate, we can handle any computation that deals with this algebra. So specifically we introduced Jz on M equal to M times M in quantum mechanics notation, but M is any vector. So you could write in vector algebra term, treating this as a matrix and this as a vector and eigenvalue. But then the interesting things were that we could realize that J squared, and this in inverted commas, you treat it as a composite symbol. J squared, its definition is Jx squared plus Jy squared plus Jz squared. Yes. So this has same eigenvalue on all the M. So this commutes with each of the Ji, and a particular representation, irreducible representation, has fixed value of J squared. So we can say some bulleted things. So J squared equal to this commutes with these, and a particular irreps has fixed values of J squared. Also Jz has to have highest and lowest eigenvalues, so that the values of M are bounded. And then we could also prove that J squared is equal to L into L plus 1, where L equal to M max. Also M min equal to minus L. And finally, of course, if M is an eigenvalue, then M plus minus 1 also are. That should actually have been the very first statement. M plus minus 1 provided not 0. At some point they do become 0. So this is sort of the first one actually. Basically these are the facts which we proved in the last two terms. and this gives us a complete control on a particular representation. Any particular representation is given by the highest value L, and then given L, so we have a spectrum. This is the word people use. For a given irrep, spectrum of eigenvalues minus L plus 1 up to L minus 1 and L. So, i.e. 2L plus 1 eigenvalues and that many eigenvectors. So, the point is that the algebra will only mix these. You can construct the raising and lowering operators J plus J minus, and they will convert one vector into the other, and this forms an irreducible representation. But there are infinite number of irreducible representations. One for each positive integer or 0. Okay. Or L equal to 0. L equal to 0 is an angular momentum 0 eigenstate. And I mean it's a trivial representation which would be something that is completely isotropic. So, it shows no it is the trivial representation, that L equal to 0 is the trivial representation. Trivial irrep, as we know, trivial irreps are important in counting everything. So, this was the summary about the angular momentum algebra. And of course we went through topology of SU2, SO3 and all that. Right. The last comment of course is that L integer, so this is where I made a mistake. So, for each positive integer L equal to 0 or each positive half integer half, 3 half, etc. So, of course when half, 3 half, etc. are included, so in physics we get the so called orbital angular momentum has integer eigenvalues L h cross, while spin has the half integer eigenvalue. Spin can have either integer or half integer. And so, because this is related to SO3, whereas we also discover spin intrinsic instead of orbital, integer or half integer eigenvalues. But one of the two in any case, because anyway, or okay, it can have integer. Given a particular system, it has either integer or half integer eigenvalues. It is also found that in relativistic systems, you cannot actually distinguish between so-called intrinsic and orbital, and only the combination J appears. Okay. So this can be either integer or half integer depending on whether S is integer or half integer. In the case of electron, therefore, it is always half integer because L is integer and intrinsic spin is half. S equal to half H cross. So now what we want to do next is to go to Lorentz boosts or the special relativistic transformations. Yes, I just wanted to make a comment here because spin is a very puzzling property. In relativistic field theory and in the very high energy experiments, we never find any structure to the electron. So there is nothing rotating there. There is nothing, no dimension to the object. So what spin means is somewhat mysterious. So note that intrinsic spin has nothing really spinning there. Because we have a point particle. No structure has been discovered to the electron. You know, electron rest mass is half an MeV. So the Compton wavelength is inverse of H over mc. So it is determined by that half MeV energy scale. But we have now explored the electron to 100 GeV. So that is like 10 raised to 5. It's like million times the mass of the electron. And it has been probed to such scales much smaller than its Compton wavelength, and it doesn't reveal any structure to it. So electron has never revealed any structure experimentally. Much smaller than lambda Compton. However, this mysterious intrinsic angular momentum does add to the orbital angular momentum in the case of hydrogen. So the spectrum of hydrogen gets classified by J and not by L. Okay. So that is the big mystery. sometimes people say that in history of quantum mechanics, Dirac came up with this slightly strange looking equation called Dirac equation, which I hope to derive if we can, because it's only group theory actually. There is not much physics real as far as the free Dirac equation is concerned. It is the lowest dimensional representation of SU2. And lot of people think that if you do special relativity, then because Dirac equation was intrinsically relativistic and had spin bundled in it, therefore spin is an intrinsically relativistic entity, which is of course true. It is intrinsically relativistic because everything in the world is intrinsically relativistic, but that it necessarily follows from special relativity is not true, because you can have special relativistic spin zero particles as well. So special relativity does not imply half integer spin. Okay. So accommodates all values of spin. This much statement I can make. Of J, 0 or half or 3 or 1 or 3 half, etc. So this 3 half and higher things usually occur in nuclear physics. You have nuclei, and nuclei have some total spin which can be large also. It can be 13 by 2, it can be, I don't know how large it gets, but it can be large. But the half integers, but those are composite objects, you know they are composite, and so there you can actually try to think that something is spinning, but as you know in the end the intrinsic objects don't really quote spin, so we don't know what it is. We had, if you remember, a talk also a couple of weeks ago on where is the spin of the proton coming from and so on. So the mysteries sort of remain, but it is not true that relativity implies that there are spin half particles. Relativity allows all of them and doesn't select between them. So now we want to go to the relativistic symmetry algebra, and this is called the Lorentz group. Lorentz group, we include both space-like rotations as well as boost, velocity boosts. I don't know who invented the term boost, but it is very popular. It's sort of to remember that you are not actually accelerating a frame to the other velocity. You are only transforming to other value of the velocity. So it's just instantaneously, there is nothing happening in time. It is just change of frames to another frame which has a different velocity. Let us try to recall special relativity. I hope that you have done this and are already sick of drawing this diagram, but here it is. So we draw this y, although it's not really needed in this picture, x and y, x prime, y prime, and this is a frame s prime moving with respect to s at some velocity v. Okay. So s prime velocity v. In this case we say that the transformations are, and note that I am going to write differences of coordinates. It's sometimes confusing if you write x and t. It is more correct to write delta x prime and c delta t prime. So the transformations are on differences of coordinates. Origin should not actually matter. Now we know that the way this transform is gamma times delta x, and here I have to make a choice. So we will say plus V by C, so we call that parameter beta, times C delta t, and C delta t transforms into gamma times C delta t plus beta times delta x, where beta is V by C. Gamma is 1 over square root of 1 minus V squared over C squared, 1 minus beta square. So we have restricted to xt transformations to keep things simple. Now what is nice about these transformations is that, did we do this a bit earlier? We introduced that cosh and sinh notation for this? No. Okay. So now we can, these look rather mysterious, but actually they are just rotations of they are rotations with a graduate degree, okay. Slightly more sophisticated looking rotations or slightly more upscale rotations. So we define, so let this factor beta be equal to tan hyperbolic of some object, some symbol psi. So the point is that we are looking here at two quantities, gamma and beta. Typically in the transformation it will be gamma times this, gamma beta times this, but gamma is nothing but again related to beta. So we want, there is only one parameter. So what we are suggesting is that better parameter to use is something called psi, which is tangent inverse of this, such that then gamma factor, which is equal to 1 over square root of 1 minus beta squared, becomes equal to cosh psi, okay, because 1 over tan squared, so you will put 1 minus sin, this is sin squared over cosh squared, so cosh will come in the numerator, and 1 minus sin squared is cosh squared, so we will get square root, and so this becomes equal to cosh. Sinh psi is product of the two, so gamma beta is equal to sin hyperbolic psi. So just to draw a little picture, what we have said is that I have a parameter psi. As a function of it, this beta parameter will be tan hyperbolic, so it will be saturated between -1 and +1. Okay, so the beta will look like that, because anyway beta parameter is V by C, so it can't exceed +1 or -1. But then psi parameter is free to go between -infinity to +infinity. So -1 less than beta less than 1, whereas psi therefore goes from infinity to -infinity. Therefore, if we now come back to these, we can recast these as C delta t prime equal to gamma times this becomes cosh psi times C delta t plus gamma beta is sinh psi times delta x, and delta x prime becomes equal to sinh psi times C delta t plus cosh psi times delta x. Okay. Now this is just like rotating x y into x prime y prime. So we can make a comparison. Whereas here we have C delta t prime delta x prime equal to cos psi sin psi cos psi times C delta t and delta x. So it is essentially a hyperbolic rotation of time into space, because after all what you had to do was keep C delta t prime squared minus delta x prime squared invariant. So the hyperbolic rotation the inverted commas are on rotation. So this hyperbolic rotation keeps C delta t squared minus delta x squared and invariant, just as delta x squared plus delta y squared is left invariant by Pythagorean rotations. Do we call them Pythagorean? Okay, this Pythagorean metric is by rotations. Okay. So this is Minkowski metric and this is called Pythagorean metric. That is the only difference. Again, to remind you, we had introduced the rotation group as some metric preserving group set of matrices, and that metric was the Pythagorean metric. Now we have this metric, so we call this group SO31. So we call the corresponding group of transformations which can leave this invariant. SO, this is special orthogonal, but 3, 1 because the metric signs are like that. So we introduced eta Many people quickly write a big 0, but I had a professor who always insisted that one has to fill it with zeros. So this is the Minkowski metric, and that is left invariant by these hyperbolic transformations. We have written, of course, only the Tx, but likewise there are also Ty, Tz and Ty and Tz transformations. So we can put Ct y and Ct z boosts. Parameters would be then psi x, psi y, psi z independently for each of those boosts. So SO31 has totally 6 parameters. So we could have called them psi1, psi2, psi3 also, theta1, theta2, theta3, the 3 rotations and the 3 boosts.